we live? Let's see. Are we live? Hello, hello, hello world. Howdy doody. Howdy doody. Welcome, welcome. Yeah, my voice will be like somewhat. I guess I'll raise the volume a little bit just because I'm kind of tired. I don't want to talk too loud. I kind of want to go to bed. Like, I'm both sad and tired, I guess, at the same time. Very sad, very tired, just thinking about different things that are difficult to think about. Kind of upsetting. So what I wanted to do is just say hi. Start with that. Hello. Welcome. Yeah, I'm get pretty sad sometimes. There's a lot to say, there's a lot to talk about, there's a lot going on, there's so many things. But for me right now, I'm just kind of waiting. There are some things that I need to take care of that are important. I just gotta go one small step at a time. Small, slow step. Just very slowly, just inch my way forward. And then once I get to where I gotta go, then I can pick another direction to start inching my way forward. Oh man. But in the meanwhile, habits are important and continuing with things are important. And one of the things I'd like to continue with is, for a long time I'd wanted to solve these math problems online. And I would like nothing more than to have no problems or issues or anything to pay attention to or to deal with, and just bang out all these questions. Alas, such is not the case for me. I have problems that I've got to deal with. Difficult problems. Difficult problems that I don't necessarily know if I even have an answer to. How to solve them, how to fix these things. What to do, how to do these things. I don't know. I don't know, and it's fun too because your problems pile up. I lost my credit card today, and I found myself blaming other people. More likely than not, I just lost it. But there was this moment where I left my wallet unattended, where there were other people, and I thought, what are the odds that someone's going to steal my credit card? Don't do that. Don't do that. I mean, there's not really much of a problem other than grief today, on top of the other things that I was already frustrated about today. There are so many things to be upset about. That's something that the pastor from the church that I've been attending lately, he was talking about not sinning, and in particular bridling your tongue, not saying things that you shouldn't say, and things of that nature. And I think about that, like how many times you're frustrated with someone, you want to say something nasty, or just not be, I don't know, or even someone treats you unfairly and you want to, deride that person or something, or complain about it or whatever. Things of that nature. I mean, there was a lot. There was a lot that the preacher talked about. I think there were 5 rules. Try to try even for one day to maintain these 5 rules with regard to keeping your mouth shut, basically, keeping your tongue in control. It's constantly deadly poison. But what does that have to do with my credit card being stolen? Well, the idea was basically that you kind of shrug off the frustrating things that tempt you to spew poison, basically. And I would say this is kind of a similar thing, where even in my mind, I'm like ready to start spewing all kinds of poison about, just in my own thoughts, my own poison about the people that I'd left my wallet near unattended. And again, more likely I just lost the card. More likely. But here I am, committing sins in my own mind. It's just... and it's such a, like, it's... it really could be nothing. And that'll get me to sin. Get me to sin. But the same is true for even the things that genuinely are difficult and frustrating in your life. You know, it's like, why would you be evil because of these things? And like, even if someone did do something evil to you, right? Like we're talking about not even just difficult things, but like someone did something evil to you genuinely. Like it was, it happens, right? Like it's kind of rare. Typically, it's either out of ignorance that bad things happen, or don't attribute to malice what you can attribute to ignorance, right? It's usually it's not malicious. It's usually just chaos, ignorance and chaos, and the ensuing chaos. But even if it is, it's like, someone if someone did genuinely go out of their way to swipe my credit card, who cares? Even if it was something like, I lost $5,000 because of it or something, or like even if it was like something, I don't know, lost a foot or lost a hand because of something that happened, or lost an eye. Why be so worked up about it? Why be so upset? Why be so frustrated? What's the point of that? Although I don't know, I'm yeah, suddenly I want to talk about like real things that I've lost that were pretty heavy. Let's not get into all that. Anyway, I don't know. I like to just kind of chat before we get into these videos. Just get a couple things off my mind. It feels like I wasted the whole day. I just feel like my whole day was just, I don't even know. I feel like I've had too many days like that. Like I like to feel like I'm at least productive. Like I'm at least doing something in my life, and I'm not just like wasting away. But today was not one of those days. Today was one of those days where I just felt like didn't make very much progress on those very important or seemingly important things. There was something I thought about philosophically that I don't really want to get into here, but I don't even know if I want to talk about it all on a video, but something about like basically my future, I've had a lot of anger and resentment and frustration with regard to thinking about my future and thinking about other people involved in it or not involved in it. And I just have like, I sin a lot, basically thinking about myself and my future. Sin against other people, sin against God, and I've been thinking about that, and there's like things I realized, like a lot of the things that I'd focused myself on that caused me to be like that were vain things, in the sense of like, you probably not probably not like things that you wouldn't normally want to have, I guess, or want or expect in your life. However, fully realizing like, well, look, maybe you're not going to have those things in your life. Like maybe it's not going to go that way. Accepting that, it's like, well, actually, who said you're supposed to? Why do you think you need to have these things? Why do you think you need to rush into all this stuff? Why do you think, where did you who told you that this is what you should be doing? Who told you should be getting into all of this mess? And it's funny too, because I realize I really should make a separate video where I'm talking about this stuff, but to give it more context. funny thing I realized is like not only did I just randomly decide on my own for my own vanity's sake to do these things that got me into a lot of trouble spiritually, but also upon further examination you realize none of those things could have worked anyway. Like they were like basically I was in the wrong side of town for years. And there was never anything good that was going to come of it. Like it was never a good idea. The people that I was dealing with were basically wanting nothing but to take advantage of me. That's it. Like I'll make a video I think at some point possibly. I don't want to make any promises, but I probably will put it into a video or think about it, try to. The problem I keep running into now is like I want to do things, but I also like feel like I shouldn't waste time because I have these problems that are like really difficult for me to kind of make headway on, and I'm like, man, I really need to focus on those things. Like just because it's hard doesn't mean you can't do it. Like you gotta focus on it. You know, you'll figure it out. You just need to stay focused. But anyway, what was I saying? Yeah, I just been realizing that like actually I've been going the wrong way for a long time. I go the wrong way a lot. And I sin because of it. It's like in these tempting things. Like I don't need to be tempted like that. Like what are you doing? Why are you tempting yourself? Who told you need to do that? Who told you to get upset about that? Who told you to yell at this person? Who told you to be upset with yourself? Who told you to be upset with them? Who told you to pursue this or pursue that? Who said you should? The world, they told you to do these things because the world is owned by the devil and he loves to watch you run on a treadmill and suffer, I guess. Get on some treadmill and suffer. Loves to tempt you. But these things didn't come from God, certainly not. In fact, if I was doing what God wanted, I would have never run into those things that seem to be so painful for me. But yeah, so here I am. I turned the volume way up, and now I'm talking a lot more loudly. All right, well I could lower it a little bit now. I don't know. Yeah, I think it's fine to I think it's fine to talk normally. I think it's okay. It's just I wasn't feeling too good just a few moments ago. It feels good to just speak about it a little bit. Yeah, I'm sad. That's all. I mean, I'm sad. You know, there's plenty of things to be sad about, though. You don't need to be sad. Don't need to be sad. So here we are. Take a look at this problem again. Wiggle sort. And very interesting problem. I wanted to go over. So we solved it already. Like we're in good shape. However, we are a bit slow, you know, a little slow in our solution. So a couple of things, there were like a list of things I wanted to do. So one thing I wanted to do was save this, because I like this. Save this. Be full screen because I have this tendency to want to save this and end up freaking doxing myself. So where do I want to save it? Documents? Yeah. No. No. Oh. Yeah, we'll say actually hold on, let me find a place to save this. Yeah, okay. So okay. Sure, alright, so save this. Let me show you what I'm doing. Go back to showing you what I'm doing. Yeah, so save this. Let me see if I can code up another solution. Let me see how long it'll take me to do it. Do this. If I wanted to do this, like if I didn't have a lot of time to program this, right? That kind of thing. So I want to sort. Standard vector ret. Nums.size, same size, all zeros. Could do, yeah, I equals 0, j equals nums dot size minus 1, nums dot size over 2 plus, maybe better do this. And I equals 0, j is here, this index. And what you're going to do is just thinking how to do this properly. I'll do an A as well. This is probably easier. No. How do I want to do this? Yeah, it's really... Just thinking how to do this properly. I was kind of struggling with this before. Like trying to think of how to do this. You're going to push back the smaller number and then the larger number. And you want to say, you're actually going to increment both of these. You just want to say I is less than n. That handles. Hold on, let's see what happens here. Forget to compile. Wait, what? One, 2, 3, 4, 5, 6 divided by 2 is 3, 0, 1, 2, 3, 0, 1, 2. Oh, I don't need to do that. I'm sorry. Oh, come on. That's why. I'm sorry. It's my mistake. Okay, it's probably correct then. This is I was supposed to do this a little bit faster than that. This is only supposed to take a couple minutes. Instead it took like 5 or 10 or whatever it is. It should have been like very fast to code this. I think it's got to be at least one. Yeah, it's got at least one. I'm a little nervous to submit this. Well, we'll go for it. See how we do. Oh man. I hate to see that. Oh man. That's ouch. Ouch. Should have tested that one. Yeah, I was thinking about it. I was like, I don't know if this handles every case properly. I wanted to test it, but I also didn't want to take the time. What do we do? 4, 5, 4, 5, 6. This is wrong. Should be 4, 5, 5, 6. Oh wait. Oh, no kidding. No. 4, 5. Oh yeah. Oh yeah, this is wrong. It's the wrong algorithm. Huh. No kidding. Wow. Imagine that. Here I am thinking it's right. And it's definitely not. Definitely not. Huh. Huh. No kidding. Wow. Maybe, yeah, all right. I think there's still a way to do this. It's almost the same thing. Just start these at the other side. Excuse me. Excuse me. Something like this should work. See how it goes. Oh, okay. Yeah, it works now. I want to test a bunch. I don't want to test things. I just want to go for it, see what happens. Hey, there we go. Okay. See, that's a lot faster. I thought that would be faster. Something about this is just efficient, you know. I feel kind of bad that I didn't code it correctly the first time. That's actually like upsetting. Because I was like, oh, it should be like really easy to code. No, not if you do it wrong, do the wrong thing. Yeah, basically you just sort it and you pair up the larger values with the larger values, the smaller values, the smaller values, right? So there's a smaller list and a larger list. Break it into two pieces: smaller list, larger list, and sort of left to right you have these pairs of smaller values with larger values. You kind of pair them all up. And the mistake I made is that if you do that, you can end up in a situation like this, which is not what you want. So what you do is you do this, you do what I just described, except you do it backwards. So the pairing is left to right, but you actually move the pairs to from the right to left. So you pair up 5 with 6 and put that on the left side, and then you do 4 with 5, put that next to it on the right side. So that way you would have, basically you would avoid situations like this, where you could end up with pairs next to each other where the values are actually equal, 4 to 5, 5 to 6, 6 to 7. If you do it the other way, then you can guarantee that you always have a larger number before a smaller number. And you're in good shape. Now, here's a question. I wonder if you could just simply run a... Now, no, so you can't do this with a quick select routine, because in the quick select routine with the partition across the order select of the order statistic, the problem with doing this with a quick select routine is the first problem is that this pairing that I'm describing is very difficult to do in place. I guess it's kind of challenging to do that in place, I suppose. That's sort of one problem. And the other problem is not only is that difficult to do in place, but it's also not only is that pairing difficult to do in place, but it's also not necessarily going to work out the same way because it's not sorted. You could end up with, you have the smaller value, larger value, and then you could end up with two smaller and larger values, which happen to also just be like 5 and 5. So you do run into an issue. But this would be how I would do it if I didn't have these constraints. So this is n log n time, and it's linear extra space because we create an array that we push everything into. And so, yeah, I mean, this is like really simple to understand and really straightforward to kind of code and all of that. Pretty quick, but as you saw, like, I actually got it wrong the first time. I had the wrong idea, which is kind of annoying, but so I missed a kind of a test case, I guess. Yeah, I thought about that a lot too. I thought that was right. I thought I had that, but nope. No, sir. So now, and obviously this is to handle the case. There's a difference between the odd case and the even case. Something to consider. So, okay, so that's one way. So now let's look at the discussion, right? So that was the first thing, is I wanted to solve it sort of how I would do it quickly how I would do it, if I wanted to use less time to solve it. That's one thing. The next thing is the discussions to find out how you would solve it, how other people did it, because I can guarantee other people did it in a smarter way. And then I also wanted to rewrite my quick select routine with the partition routine, right? That whole bit with the random engine, the randomization library, right? Utilizing the randomization library. And what else do we have? Also, we have the randomization we want to do. The other solutions we want to do. And I also want to do the randomization portion first. I also want to, there was one more thing I wanted to do. think I probably would just write like one of their solutions again. I don't want to write my solution again. My solution was freaking, oh, there's so many pieces to it. The basic idea was similar to this pairing thing where you basically wanted to pair off numbers that you knew were sort of no good, numbers that you knew were, you kind of wanted to pair off the median. You know what, maybe would have been better was actually to just thinking now, it may have been better to find the value of that order statistic, and then you could do a three-way partition where we'll find that order statistic, and the partition you'd be able to find out how many to the left you need to sort of pair up with larger values, and then you could partition again, a three-way partition, which is sort of all the numbers smaller than the median, all the numbers larger on the right side. I guess it would yeah, you could do a three-way partition, which is kind of neat thing to do, and then you can pair off and move all your values appropriately. And maybe it would have been a good idea to three-way partition the median values on the left side, the smaller values in the middle, and the larger values on the right side. And what you could do then is then make your swaps appropriately, so that you sort of move your larger values, intersperse your larger values with these different, I guess if it was like 5, so 5, you have a whole bunch of 5s on the left side, and well, really, I guess the simplest thing to do is collect the number of 5s that are on the smaller side and place them, count how many there are that are to the left of the median index, so count them, and then place them throughout the array in the right spots, right? Basically, I'm just thinking, how do you do this? You would place them right to left. That's the way you would do it. So you would start, so you can, when you count them, shove them all to the left side, and then what you're going to do is set a pointer to the sort of the right side of that list, and then you can start moving them to their correct positions where they would be in the array. And then you can do another pass right to left and grab each number that's larger than that median value and place that left to right in the right spots. Right? If there isn't something larger, put it in there. And then now what you're left with on the right side should be all of the smaller numbers, or basically a mixture of smaller numbers, larger numbers, like the leftover numbers that weren't used, larger numbers that weren't used, and smaller numbers that were moved in over there. And also, like I said, 5 was going to be the median, sort of that value, and then a few extra 5s that were sort of in the larger side, on the larger side. And then from there, now the tricky thing about that is that you would not have used any of the smaller, oh no, you would have used smaller and larger values. Yeah. So actually, yeah, your median value should still be the same. So you can do a quick select again on what's left over there, and then I think I described there's a routine you can run that's that's very simple, that can set that portion of the array up correctly. It's basically the same algorithm that we did before, except done a little bit smarter, we'll say. Done in a way that's easier to understand, easier to code, a little bit smarter. Yeah, I'm wondering if I should try to code that, because in theory that should be pretty quick. That should be pretty quick. I'm not sure how quick it'll be, but in theory it should be relatively quick. Just thinking. Whoa, no. Yeah. Let me think about this here. Just thinking. Move the smaller values to the left side. Yeah, and then spread them largest, yeah, right to left. And then put larger values as much as you can into the correct positions. Pretty interesting. Pretty interesting. And yeah, what's left over you can do a quick just quick select and you should be done. Thinking, you know, the only issue I have is it seems, yeah, I guess the other routine that I was running was just kind of expensive. Like it was still linear, but it was just expensive. I think doing it the way I just described would be better. I kind of want to code it just for the sake of like, I don't know if I want to do that tonight though. It's like, oh, it's like a lot. I probably would want to include like subroutines for like find next large value, or like, yeah, like a routine, the subroutine to move median values over to the left and count, something like that. Probably wouldn't even give a subroutine, just give a comment for what that piece of code does. Yeah, anyway, so, okay, so let's look at the discussion, what they have to say. Pretty interesting problem, pretty good problem. O of n plus O of 1 after median virtual indexing. What is that? Index mapping in Java, Python explanation proof. Oh man. Whoa. 2015. 6 years ago, Pachman. Man, I feel like I'm late. You know? I feel like I'm late to the party with this. Summary of the solutions for your reference. Details, explanations. After median. Without virtual indexing. Simple C++. Deterministic linear time. Quick select and median and mediums. Wrong. After careful consideration, one realizes you don't have constant memory if you use median and medians. False. quick select and virtual index. Oh, no kidding. 100% solution. No indexing required. Simple modular solution? What? Average linear times C++. Easy to understand. Clean. Oh boy. About to get destroyed here, huh? We are about to get destroyed here, huh? Alright. Virtual indexing technique. Not sure. I'm not the first to come up with this. Couldn't find anything about it. Made up a name. Order statistics is probably what he's thinking of. Three-way partition to wiggly in O(n) time O(n) space. I was gonna say a three-way partition would be good. Wow. Excuse me. Okay. Three-way partitioning. Yeah. I mean, three-way partitioning is some things you can do. This is pretty neat, pretty clever what he did here. Like, this is way better than what I was doing to make it wiggly. Oh wow, look at that. 1 plus 2 times I modulo n or 1. Find a of I. Interesting. I think he did what I did, where he put these, he paired off the larger values and put them on the left side first with the smaller values. Something like that. I don't know what he did. I don't know. So I want to say this nth element idea. Oh, so this is, oh, I see. Okay, no, I'm sorry. So this is his virtual indexing. No, okay, that was a little cocky of me, a little bit arrogant. So he calls it a virtual index by assigning a, what do they call that? Actually, C++, this is a preprocessing, what do they call that? A preprocessor command. Yeah, command to the preprocessor. So this is the virtual indexing. Oh, that's neat. Find a median using nth element. The only guarantees average time. Right. This is quick select. What comes after that? Three-way partitioning to arrange the numbers so that those larger than the median come first, and those equal to the median come next, and those smaller come last. Ordinarily, you then use more phase to bring the numbers to their final positions to reach the overall wiggle property, but I don't know a nice constant space way for this. Instead, I embed this right into the partitioning algorithm. That algorithm simply works with indices 0 to n minus 1 as usual, but sneaky as I am, let me wipe my face. Yeah, Pachman's always got some pretty clever ways of doing things. It's always impressive. So algorithm simply works with 0 to n minus 1 as usual, but sneak as I rewire those indexes where I want the numbers to actually end up. The partitioning algorithm doesn't even know that I'm doing that. It just works like normal. It just uses a of x instead of nums of x. Let's say nums is 10 through 19 after nth element. And ordinary partitioning, we might have 15. This is my median. I rewrite it so that the first spot has index 5. Excuse me, second has index 0, etc. So I might get this instead. 11, 18, 14, 17, 10, 19, 13, 16, 12, 15. And this is perfectly wiggly. And the whole partitioning to wiggly arrangement, everything after finding the median, only takes linear time and constant space. Above description is unclear, maybe this explicit listing helps. Actually accesses nums of 1, nums of 3, nums of 5, nums of 7, nums of 9. 0, 2, 5, 4, 6, 8. Yeah, so before I was talking about a bijection, I was trying to kind of encode a bijection into this. That's basically what he did, is this bijection. It's interesting that he could have written a lambda function that does this to convert, from here to, from x to what he's looking for. But actually, yeah, I mean, this works too. This is pretty interesting. My bijection was different. It was, right, for me it was if I was less than the median value, then you would multiply by 2. If I was larger, but actually mine was wrong. He should have, right, so he started with the odd values, the larger values, and then the smaller values. So it kind of, yeah, really different from what I was doing, but really interesting. How the heck did he figure that out? Apolloides, solution Apolloides. Partitioning algorithm already, but I didn't know the name. Apolloides idea to partition to reverse order happened to make the index rewiring simpler. Yeah. That's pretty interesting. So yeah, there's a 3-way partitioning that exists you can do, and he's just saying do larger, median, smaller, and then also use you're going to map the partition instead of larger, median, smaller. You're going to actually interweave the values. That's pretty wild, man. I should really think about that. Like, firstly, the partition, and then secondly, how one can. This is really clever. I mean, this is kind of like a little. I don't want to say it's beyond me, but it's like this will take me some time to kind of ponder and think about, like, how to do this, how to come up with this. Yeah, definitely, right, definitely. The 3-way partition, I don't even really know how to do that, quite frankly. But obviously, this is quick select, this part. And excuse me. Now, there's a few questions. The first is partitioning in the first place, larger, medium, and smaller, larger, medium, and smaller, or larger, middle, and smaller, large, mid, and small, we'll say. That I'm not super familiar with, that partitioning. I've seen that before, but I haven't actually coded it. I think I coded it once, something similar, but I would need to kind of review that again. And then what you do is the indices themselves that you're swapping and moving around, you're actually going to basically map everything to a different index altogether. You're going to be working with different numbers. Well, I guess what's interesting about this is, like, what you need to, in order to be able to do that, you need to know that the partitioning algorithm is more or less independent of which indices you actually are moving around, if that makes sense. which it is. The logic is you only compare it to the midpoint. And so if it were the index, the nums themselves, so yeah, actually you're actually operating on different numbers altogether rather than, or different indices altogether rather than sort of, it's almost like you've encoded the wiggle portion already, if that makes sense. You've encoded the wiggle portion already. So when it's finished, it's going to have that mold that it kind of fits into. That's really interesting. That's like a really clever way to do this. It's a mapping, yeah. Yeah. Yeah, I mean, that's what I did too, the bijection. Although I did it the other way around. The 0 to mid, in his case, 0 to mid are the larger number. I guess that's probably why his bijection is simpler than mine. It's because he put the larger numbers on the left side and the smaller numbers on the right side. I wonder if you still run into the same issue though, where if you have a lot of duplicates, that this fails. I don't think so. I think the reason why it doesn't fail is because actually you might be able to get this to fail in some test cases. I want to say yeah, man, I don't know. I'm not sure about this. I really think if you had a lot of duplicates that this would fail. I want to say that's the case. I think so. Like a lot of duplicates that are on the left side and the smaller side. Or even just right in the middle, even. A lot of duplicates that are sort of even on the smaller side, even on the larger side of the partition. I want to say that you actually could get that to fail. I think the key is because of how this is set up. In my case, what I showed is that actually the median doesn't end up in a row. In other words, like this three-way partition, you would have all of the large numbers in one section, all of the median ones in a section, and then all of the smaller ones in another section. I didn't have that guarantee before when I did my quick select, and it was causing issues. And what I want to hazard a guess that if you do guarantee that these things are sectioned in that way, then actually this won't fail. And the reason is that you would be pairing off the larger values with those smaller median values left to right on both sides, if that makes sense. Yeah. So you would actually be doing what I did before with the sorting. You do something similar where you don't actually need a full sort, because as long as the larger portion is just bigger than the median portion, then you're in good shape. So you don't even need this also, by the way. I mean, this helps. You basically end up doing the same routine that I did on the sorted set. The same routine that I did on the sorted set at the end there you saw. Well, actually, no. No. Actually, this is really clever. No, I take it back. You do need to do something clever like this in order to do it in constant time, right? That's what I was saying. I was like, oh, when it's sorted, how do I how do I move the elements into the right spots? And really want to sort it in reverse and basically do this routine. Three-way partition that also rewires where these indices end up. Rewires which indices that you're manipulating. That's very interesting. That's super interesting. I don't know, man. You think about it. I might come back for another part 4 on this. I kind of want to stop and kind of digest this a little bit more. So now here's a question. Could I have paired off my values? Let's say I sorted everything in reverse. Because I paired off my values into a new array, but maybe there's a way to pair off the values into the... I think this might be the only way to do it. This is like freaking voodoo magic, though. This is like witchcraft, man. If there's a way to pair off my values in constant, without using the array that's been sorted in reverse, we can obviously we know that this routine would work as per Stefan, but is there a way to do this that's like a little more direct? I don't know that there is. You basically partition again. However, if you're larger than the mid, then you're going to swap these two values. A of j is larger than the mid. Swap a of I and a of j and increment them both to new values. I of 0 starts off at, these are both starting off at the same spot. So these end up looking at zero. We said 0 to the mid or the larger or the odd number. So they both start off at an odd number. And this should be greater than the mid initially. So you swap these and increment them both. They're both greater. They should both be greater, I think. Shouldn't matter which one's on which side. And then if you're less than, then you don't increment j. Now increment both of these, and where do they go? They go I is 0, which should go to 2 times 0 plus 1, so 1 modulo. And depends if n is odd or even. It's modulo n1. N is even, it's going to be n plus 1. If n is odd, it's just going to be n modulo n. That's kind of interesting. Not really sure about that. If n happens to be even, that you take this modulo n plus 1. Not sure if that really does anything. Not really sure if that matters. Your or with a 1. Yeah, I don't know. I don't know what that does exactly. Not sure about that. I mean, apparently it's important to have that extra or 1 there. However, that doesn't seem super important. Because, yeah, if you're even, then that actually goes to n plus 1. If you're odd, that just stays at n. But why would you have n modulo n plus 1? that all that could do is just throw you off the edge, quite frankly. I want to say, oh, I think it's because I see. Okay, wraps back around. I see that makes sense. That makes sense because we're doing 2 times I. The values, once they get past the midpoint, when you double them and add 1, right? You would, okay, I see now. Now I get it. Now I get it. You do. Okay. Has to do with. That's interesting. So it's actually the modular arithmetic is really just to wrap back around. That's all. Pretty clever thing to do. Use a modulo with an or of a 1, right? So anyway, so when you're looking at 0 and 0, these we don't really care. Yeah, that's kind of interesting. And then we add 1, go to the next one. So we start off at 1, and we go to 3. Should be the same deal. Should be the same deal for a while. You just kind of swap around back and forth the larger values. And then once we start getting to the median values, or the median values, or even the smaller values, that's when we start incrementing j, and I doesn't increment anymore, so now they're not looking at the same value anymore. Oh, this doesn't do anything actually for a while, right? Because I and j are actually pointing to the same element, so it just swaps them both with each other. Then you get to the midpoint, and then now you start swapping values between each other, and odd and even values potentially when you're equal to the mid, and you increment j. So the next odd value, let's say like a lot of values let's say there are like a lot of the smaller values are, yeah, there's way more a lot of smaller values and a lot of midpoint values, median values, right? So you'd only do this a few times, this routine. This portion would only happen a few times, and then you would start incrementing j, or you'd increment j once. And what does that look like? So then you'd say a of j is equal to mid, and you would increment j again. So that would be, it's also the odd values for a while. So for a while, you just kind of skip j ahead, and I stays where it was with this value that's larger than the mid. And then, let me just see, where's my volume? I think my volume's okay. So you do that. So this is just going to keep going though until you hit something that's not equal to the median. By the way, I'm assuming we're working on something that's already been partitioned. Makes more sense if we look at something that's already been partitioned, but something that's not been partitioned, this should work on, like something that's just totally as it is. Pretty interesting stuff. So this kind of guarantees that I of j, a of I, and a of j, a of I should basically stop at something that is greater than mid. And if at all, I suppose, right? Unless if it's something that's not greater than mid, let's say if they're initially, say if you're initially smaller, what happens? You move a of j to a of k minus minus, where a of k is at the end. So you move all the smaller values to the right side anyway. If you loop through a bunch of smaller values, and if you loop through a bunch of values that are equal to the midpoint, like let's say you're partitioned in the wrong direction, for instance, you would do this a bunch. All these a of k values would be smaller values. A of j less than mid. And these are all of the odd values for some time. Yeah, this is really interesting. I don't know. It's like a very unusual kind of a. Basically, you're interspersing like. This is so weird. Yeah, you're doing a. This is like really, really clever. Like I don't know how you would prove this or how you'd think of this. Prove that it's correct. But basically, if you had a three-way partition, you can show that if you paired up from starting with the larger to the smaller, you paired the larger values with the smaller values, and even if there's these duplicates in the middle, you pair them up larger with smaller in the right spots, left to right. You can show that's correct, right? That's sort of what we showed before with our sorted version. And so what this does is that you not only do partition, but you also perform that pairing simultaneously, because you're going to move the values that are going to be in the larger portion are going to be moved into every odd spot on the left to right, and similarly all the values in the smaller portion are going to be moved into the even slots from left to right, also from left to right. And the partition would normally maintain that larger, median, smaller. However, now it's going to have that interspersion going on, and also from that order, like that resulting order would be if you took those and then interspersed them accordingly, that's what you're going to end up with. And all you had to do is map the indices to get that result. That's an incredibly clever way to do this. That's extremely clever. Like I have to say, really handed to this fellow for thinking that up. Like I probably never would have thought of something like that. Like I guess there are some algorithms with regard to partitioning where you can, as he described, it's virtual. You can use virtual indexing, or we'll call it, or not virtual indexing, but yeah, you can map your indexes such that when the partition is finished, you have a special result. This is kind of amazing, quite frankly. Like I'm somewhat amazed. Like I might code this up for myself to try to kind of understand it. But yeah, I mean the normal partition would be if the values are larger than the midpoint, you swap them and then increment the indices. And then if the value is smaller than the midpoint, you would actually swap that smaller value to the end to make sure that it's sort of on the edge partition. And then if you're equal to the midpoint, then you leave that value alone, right? So interesting. J less than or equal to k. K starts off all the way at the end. So all the smaller values are going to end up swapping into the right side, which is the partition, right, all the way on the right side. And all the larger values don't go anywhere. These get skipped. And then all of the values that are equal to that midpoint, you actually move the larger values into the right spots. This is a little bit confusing. So even this partition algorithm is like not so obvious. Like even if you're just doing a regular three-way partition, why do you have each of these pieces? I guess would be the question to ask. So this makes sense. I mean, this is always, only operating between j and k. So every time you're smaller, you're always going to be moving stuff to the right and moving k down. And like that's very simple. That's kind of somewhat easy to understand. But how about when you're larger than the midpoint? Well, you would increment I and j, but you're not just incrementing I and j. You're whatever I is pointing to, whatever I kind of seems to lag behind j a bit. Yes, that makes sense. So I and j, I is going to be the index of, I guess it would be I is going to be the index of where the median values begin, the mid values begin. It's going to be just after the ending of the large values. J is going to be similarly on the other side, where it's going to be the beginning of the smaller values and just after the end of the mid values. That's where I and j are, that's what I and j are supposed to represent. And so the reason why you swap I with j when you find something larger is that j is larger, I is pointing to should be just to the right of the larger value. So put j there and then increment I, and also increment j because j is looping through your array. That's why that makes sense. And similarly, once you've actually found something, that you just leave it there, right? I you know, apparently I is where it's supposed to be. If I is where it's supposed to be, then you can just leave all those values in the really to the right of I. It should be. So this is super. I mean, this is like really clever, really creative. The three-way partitioning is not too complicated, but I've seen it before and I forgot it, but now I'll try to remember it again. I guess remember it, how to derive that. It's basically an I and a j, and you want to swap the larger values to I, and I is always just out of reach of the j, just to the right of the j values, and then so you increment I and j when you do that, and then the smaller values you want to swap them all the way to the right side where k is, and then you also want to by the way, right, you're done when k moves past j or j moves past k, and you want to move all those to the right side, and the ones in the middle you just skip for j. Just skip them. And by some miracle of maths, you can create this bijection, and not only will you still get the partition correct, but you'll also end up with the values interspersed when you're done, which is pretty amazing. Like, that's really interesting. That's pretty wild. That's not obvious at all why that works, right? Like, that's hard to prove that would be correct before actually doing it. Why you know it would be correct. Basically, you've partitioned your array, and simultaneously the actual elements you operated on, they all get mapped to different spots in the finished partition. That's really it. It is. I guess the proof is that it's just a mapping of the indices. And it just so happens that the algorithm, the algorithm works the same on that mapping. It's basically it's actually, the reason it works is that you're really operating on, if you doubled the size of the array, right? And now the values from sort of left to right are, I guess, those sort of doubled indices, and you just collapse back you actually just kind of squish it back together. It works exactly. The partition is the same, just sort of with space in between, and then you just push it back in, or map it back in. I don't even know how to say it. Like, I don't even know what to think. It's almost like it. Yeah. In other words, like the section that represents the i's, which are those are the larger values, and the section that represents the j's, which are the smaller values, right, past j and things past I. Like, each of those sections basically end up with some spacing. Excuse me. And then this wrapping backwards places them into the spots that you want them to be in. So the partitioning is the same. It's just, once you wrap back, once you use that mapping, then it ends up in the right spots, the spots where you want them to be, these values. So if you think of it without the modulo function, like, the partition algorithm is still the same thing. It still works the same way. It's just maybe there will be spaces between your values, and then when you apply that modulo function, then they end up mapped to the spots you want them to be in. That's that's really clever. That's like really hard for me to explain. Hard for me to like wrap my brain around, but like really good, really quite impressive. And the rewiring is not that complicated, but it's impressive though. Like, this is definitely really impressive. Yeah, you can actually do like a three-way partition with a mapping of the values, and that'll actually give you sort of it's not a hash, but just a kind of just a mapping of it. That's amazing. I mean, that's nothing short of amazing. feel like I'm a total moron. It's really clever, really clever. Not inhuman cleverness, but extremely clever, definitely. Hard to understand. Easier to understand. Is it really easier? I don't know if that's really easier. I'm just trying to think of like how you could prove that it's correct. Very impressive. Human mind cannot come out with this. Wow. There you go. There you go. Really hard to understand. Yeah, wow. Somebody actually had asked me about this problem. I think this is probably why. It's because it was such a difficult problem, such a challenging problem. Wanted to see if I can come up with something clever. Mine's not as fast as his, obviously, but mine is linear and constant space. However, yeah, it's not as quick. This is like really fast because it's only one pass. It's really two passes, where mine has like 15 passes or something, 20 passes. Actually, I think it's even more than that. It's like mine's a lot slower. It's a lot slower. Super clever. Let's see the other solutions. Oh, nth element. Oh, is that an STL built in? Is that not quicksort? Like, do they have that already? Partial sorting algorithm that rearranges the elements such that this is quicksort. Oh, dude. I wrote my own quicksort routine. Intro select. Oh, no kidding. I didn't know that. Brother. Someone could have told me. Come on, man. It's so funny. This is, oh, brother. Brother. That's hysterical. I didn't realize they already had a quicksort. I don't have to write a quicksort routine. They have one. They have intro select, quick select routine. They have it there already. Wow. I was gonna say, I was like, I guess he didn't show his implementation for that routine. It's because it's already part of the STL, dude. It's already there. No kidding. Why not? So where is? I don't know. How did he use it? What did he do? Hold on. Midpointer. Oh. Okay. Really? Okay, that's how it works. All right. I was gonna say, how do you specify which? It's a little confusing, but I get it. I get it now. All right. Anyway, we don't need to care about that anymore. Oh, nth element. That's all. Okay. So I could really modify my routines. Amazing. Wow. Oh wow. My sorting when I actually just sort is faster, which is interesting. That's kind of interesting. quick select if you don't use. Yeah, quick select would be constant space. The one that I wrote would be constant space. But as he said, it's not guaranteed to be linear. It's like almost certain that it's linear though. Use the simplest method. It's interesting, when I use the simplest method while the time complexity is n log n, it gives me 6 milliseconds. Really? Oh, I think this is Java. Oh yeah, optimizes the loops. Yeah, that's what I should have done. Why is mine so slow? Hold on. Yeah, I was gonna say I don't think this is the fastest way to do it. To do it this way, even though this is like super clever. I prefer to use the lambda rather than the. Well, actually, no. The preprocessor step is faster, I think. So this is, I think there's not really anything else we didn't already know, right? I think Bachman kind of nailed it. That's pretty wild. They did the tripartite. Did something similar to what Bachman did, but it's just kind of set up slightly differently. Yeah. Pretty interesting. Have to kind of wrap your brain around a little bit, but it's basically the same thing. It's just a mapping. And then here he condenses all that using. Oh no, excuse me. Use the sorting. Yeah, this is what I did too. Something like this. What I did was along these lines. And well, the virtual indexing is what Bachman came up with, right? It's from. Yeah, I'm basically just gonna end up copying what Bachman did, pretty much. There's this quick select routine. Sync with standard IO. Tie null pointer return 0. Writes his own little lambda function here. It's medium if it's n log n. Yeah, it's not constant space. Modular solution. After sorting, right? Oh yeah, you could use modulo to put the numbers in the right spot. Oh yeah, here we go. Ooh, that's cool. I like that. Oh yeah, let's do that. Sorted. Sorted. Wait, reverse. Sorting in reverse. You can, yeah, well, I mean, you can sort in reverse now. I like this one. I'll probably write that one. All right. I think, yeah, we've probably seen enough now. All right, nth element, three-way partition. This is after you've partitioned, then he does another pass, which basically maps everything to the right spots. This is what I did, basically. This is what I did before. I was describing, like, yeah. You can actually do three-way partition and then do if you do the three-way partition, you can then do what Pachman had. You can replace this with the, let me show you that one. Where is it? Oh no. That wasn't what I meant to do. Here, this one. Oh, well, all right. Basically, you can replace this sorted list here, this sorted backwards, after you perform your three-way partition with the larger on the left side, the middle, and those median ones in the middle, and the small ones on the right side. You can actually run this routine, and it'll still be correct. Which is exactly what I'm going to do. Which is exactly the point of, like, you instead of sort, yeah, you could do this instead of sorting, do the three-way partition and the three-way partition around the median, and it's faster. Technically, it's logarithmically faster. However, performing the, what do you call that? Actually, this could even be potentially faster if you do the three-way partition and then this afterwards. It could potentially be faster because, oh, actually, no, never mind. Never mind. This isn't on the same array. Never mind. You don't want to do it that way. But this sorted array, you could replace it with the three-way partition that was partitioned around the quick select element, and this would still be correct. So I think I got it as far as like what other people figured out. I guess we won't return to this problem then, because yeah, we can do sort, basically sort backwards. The way you sort backwards would be use a lambda function, and we just have int a, or just, I think it's like this, something like that. And a greater than b. And now you're sorted in reverse, and you can do j, yeah, you could say I starts off at 0, j is n over 2 plus n modulo 2, and you say I is less than or equal to n over 2 plus n modulo 2, increment I, increment j, and you do the same thing. Ret of, I used a before, right? Yeah, I did a. Nums of I, nums of j. Just j is less than n. Something like this. Does this still work? Oh. I think a runtime error. Nice. Very good. I think it's got to be less than this value. Wrong. Sweet. Oh. J and I. How? Something like this. Okay. Is this still correct? Wrong. Nice. Nice. Am I just wrong about all of this? Really, this is wrong? Maybe I'm nuts, man. Maybe I'm nuts. 2 4 2 4 1 3 1 3 1 3. Oh, and there's 3 3 at the end. Oh. What happened? Shouldn't the larger values be... Yeah, maybe I'm just wrong, man. Maybe I'm just wrong. No, this is correct. Oh, so what? It's not correct. It's not correct. Yeah, it's not correct. I can't say it's correct if it's not right. Okay, we pair 4 with 3, right? It should be 3 4. Oh, that's why. So whoa, where? Whoa. Where is this J starting here? 1 2 3 4 5 6 7 8 9 10 11 12 13. All right, 13 over 2 is 6. 0 1 2 3 4 5 6. These are the smaller values. One, 2, 3, 4, 5, 6. Yes, that's my mistake. Yeah. Okay, it starts. It's completely my mistake. The smaller values actually start sooner now. This is where. That's my mistake. Let me think about this for a second. Yes, things are reversed now. So when you're even, it was just n over 2. When you're odd, the larger section is a little bit smaller. So you're actually subtracting n mod 2 rather than adding n mod 2. There you go. And now I is going to be less than that. Is that right? No, still wrong. A little bit better. Right, yeah, it's supposed to be 3 4, not, yeah, right, exactly. However, we're still missing this portion at the end here. Is it minus n over 2? What is it? What are we doing wrong here? Or is it just this? Am I crazy? Am I nuts? Yeah, that doesn't make sense. Less than 1,000, I don't know. Let's just take a look, right? We can find out. We can see for ourselves what. Okay, let's try again. So now there's more smaller numbers. When it's odd, there's one extra. There's n over 2 plus n over 2 plus 1. where n over 2 is integer division, and n over 2 of them are large, n over 2 of them are small, and then one of them counts as a smaller value. Must be a smaller value. So you have n over 2 plus 1 smaller values on the right side, n over 2 smaller values on the left side, larger values on the left side. So j starts off at n over 2, that index, if you are, j should start off at the smaller indices, which is going to be n over 2 is the index that comes right after. If it's odd, and if it's even. I think it's actually j's in the right spot. Is that right? This is too far. I don't know, man. I'm confused now. What? What? That shouldn't matter. What is going on? What is happening here? Now I'm just confused. Now I'm just confused. That's correct. Great. Nice. Okay. Is it? Okay. Alright. I knew it wasn't nuts. I knew it wasn't nuts or completely nuts, but something's still wrong here. I should start off at 0. Fine. It should be less than or equal to, it should be less than n over 2. The thing is, if you're odd, it should be, this is so confusing. I think I have to do, okay, so you have 5 elements, right? 2 of them are large, 3 of them are small. That means the index you're going to is 0, 1, 2. 5 over 2 is 2. You're going to 0, 1, actually, for I. I was going to 0, 1, which is less than 5 over 2. J, oh, I see. Ah, that's why. Okay. J is actually the one that we don't care about. And it's actually I less than 2, and over, yeah, something like this is really what we want. Just very confusing. Okay, no, I guess not. Yeah, it really should just be j less than n. I think that's really what you need. Yeah, I will be naturally less than n. Then you don't need this anymore. Don't mind me while I'm messing around with all this. Okay. Okay, I had the right idea. I was close. I was close. Wow. 12 milliseconds, how about that? Hey, there you go. There you go. That's fast. That's fast. That's what we're looking for. Now, what you could do also is you can do the, right, you can do that, the modular arithmetic. So it's going to be ret of I equals 0 to I less than n plus I, right? And that's going to map to, how about this now? It's going to be you could do, yeah, I think it's easier to do it this way. So it's going to be 1 plus 2 times I modulo, and it would be n. However, when you're even or you're odd, that's when things get interesting. So if n is an even number, this should be no problem, right? Because if I is 0, that's a large number. That's going to go to, that's a large number, that's going to go to the odd positions. And yeah, that's really, really interesting. So, and then if I is even, that's going to go to end up at the even positions. It's not just, excuse me, the first n over 2 element, let's say we're just even, n is even. First n over 2 elements are going to map to odd numbers. And there's going to be n over 2, there's going to be exactly n over 2 of them. And they're going to map to the even indices, or the odd indices, I think exactly, right? So if you do 2 times n over 2 plus 1, you get n plus 1 mod n. Do you get 2 times n over 2 is n plus 1? Why do I get this feeling? That's 1 mod n though. If n is 6, n over 2 is 3, the 3 indices are 1, 3, and 5, right? 0 gives you 1, 2. I want to say I doesn't equal n over 2. It's n over 2 minus 1, right? At n over 2, you get back to 1. When I is n over 2 minus 1, which is the second index, just thinking the second index would be five, right? And then once you get to 3, you get 6 plus 1. Right, so that's why you have the or in there. Because when you're even, once you get to n over 2, you want to go back to 0. You want to have one extra value, kind of shove the index over just a little bit, right? There you go. That makes sense. It's when you're odd when this doesn't matter, right? When you're odd and you do n over 2 elements, they're all in the right spots. And then the next element, right, so if you had 7 elements, you'd have 0, 1, 3, 5, and then this next element, the 7th element, actually would be mod 7 would go back to 0. And that's exactly begins the smaller elements too. That's exactly where it should be. Yeah. So actually it's for the odd case. The odd case is fine. Leave this is perfect. The even case is the one where you need this. So you do something like this, which is exactly what Pacman had before. This is super efficient too. This actually apparently isn't as efficient as what we had before, just a few moments ago. Huh. It's going slow now. Oh, there we go. 12 milliseconds. Okay. I think it was just random. So sweet. So we got that speed boost now. Now, here's another question. Let's take our 3-way partition. So, you ready for this now? We're going to say auto our m pointer. That's going to be nth element, or median pointer. Yeah, median pointer, or just mid pointer. We'll call it. Yeah. All right. We'll just yeah. We're going to say auto, which is going to be int n equals nums dot size, which is going to be nums dot begin plus n over 2. Right? We're going to say this is going to be the nth element of nums dot begin with which nums dot end. We're going to so find the median, the desired order statistic. Form a three-way partition such that we're actually gonna create a copy first. Copy of the array and three-way partition array such that left smaller on the right and the duplicates of the order statistic in the middle. So this is going to be interesting. We're going to say int mid is going to be this m pointer value. We're going to say I equals 0, j equals 0, k equals n minus 1. So I have ijk, we'll have standard copy nums.begin, nums.end to ret.begin. I want to say this is how we would copy. I have to double check that. So what I was saying before is that we don't need to sort it. We can use this. Technically, this would be faster to use the quick select algorithm to find the median, and then to use the partitioning algorithm to partition into larger, medium, and smaller, because this should have the same sort of logic and reasoning for the sorted algorithm. So this should be slightly faster in terms of it's not going to be faster, but it would be faster in terms of time complexity. It won't be faster only because the constants that are involved are pretty large, or larger than sort of, I guess, the logarithmic values. Okay, so now we want to do while j is less than or equal to k, we're going to say if, we're going to call it ret of j is less than the midpoint. So the idea is that we have these I and j pointers, and we want to move them accordingly. I is always going to be just in front of the larger values, and then j is always going to be just in front of the values that are equal to the midpoint, and everything to the right of j is going to be the smaller values, and everything in between I and j should be, including I, should end up being the mid values, and everything to the left of I, not including I, should be the larger values. That's sort of what we're going to keep in mind. So if we're looking at, if it's greater than mid, we want to do this. If it's less than mid, we want to do the following. We want to swap nums of j, and we're going to increment to the next value with nums of k and decrement k behind us. Otherwise, we just increment j. So what's going to happen is, if we see something that's larger, we want to count that for I. swap it with I, so swap that larger value with where I is, put it over there, increment I to the next value, and increment J to look at the next item. If we're looking at something smaller, we want to move that thing over to the smaller side, which is all the way on the right side, and then move K to the next spot over to the next smaller position, and also J forward is up to the next position as well, because we're going to look at the next item. And then if we happen to be equal to that mid value, then we just look at the next value of J. We just leave it where it is, because all we're going to be doing is moving things to I or moving things to K, and the things in the middle we're going to leave. So now that's our three-way partition, and then now we should be able to copy elements into, or rather map the partitioned elements into their desired positions. Let's see, does this work? Variables incomplete type void. Also, what does, how do we, I don't use this very much. Void, nth. Okay, I see. Got it, understood. So the nth element's actually, I see now. Okay. It gets updated. Let's try something like this. Yep, there we go. And I think it should be correct, if I'm not mistaken. Although I seem to be mistaken. Seem to be mistaken. Really? No. How do you figure that? No kidding. And here I am thinking that this partition should still work. I want to say it's probably, might be something like this. Might be the reason. No. No. 232311. Actually, yeah, the second one is wrong too. So I was wrong about this. This doesn't seem to work properly, and I don't really know why. Let me see something before we do this. So maybe I'm wrong. I thought I was being clever with this, but I am being wrong. Oh. Oh, that's probably why. Or it could be part of the reason why. No. No. This is not right. So we partially sort nums, and we want a new array. We'll call it, or just array. I gotta sneeze. I think I just did this wrong. Or not, I don't know, maybe I did have it right before. Something like this. Oh, yeah. One of the many perks of if you change your variables, the problems you'll run into. So wrong. That's very interesting. Four, 6, 5, 1, 1, 1. Huh. Now that is super interesting. Not what I was expecting. 4, 6, 5, 1, 1, 1. 2, 3, 2, 3, 1, 1. No, definitely not what I was expecting. Interesting. I don't mean to be trying to dox myself out now over here. Let's look at potential companies I might want to work for. So I didn't want to save that to the desktop and close it. Maybe I'll just do that. So I don't potentially dox myself. I like compilers. There was a compiler job out there, and I was like, could be interesting. All right, anyway, let me go back to what I was doing. So I'm wrong about this. I thought I was right about this. Why? Oh, that's why. Oh, no. Yeah, what? Okay. 611451. You're kidding me. Does this already need to be partially partitioned? I don't think. Is that it? I thought this would work in any random unsorted configuration. Maybe I'm crazy. It does, actually, it does work. Yeah, these are larger than 465. Oh no. Wait a second. 111456. What is this value? No, this is incorrect. Uh-oh. Maybe I'm nuts. I want to say this only works on it if it's partially sorted already. Uh-oh. Uh-oh. No. Oh, my eyes starting to hurt. Oh, my eyes hurt. Stare at the screen all day, maybe? I don't know. Could be. No, this is not, oh, that's why. Brother. Of course. Okay. Yes, that's what I thought. This is still wrong, but confusing things. The median value, I think, should be 4. And wow, my body, man. Yeah, 4. Okay, that's a lot better. So this bottom one is wrong. This top one's a lot better, though. It's at least correct these top two, but this foul 2 at the bottom, that's not correct. Not only is this not correct, it should be 1, 1, 2, 2, 3, 3. So 2 is the right number, but the partition 2 on the left side is not in the right spot. Why? Yeah, so that 2 is not in the right spot. That's supposed to be 3, 3, 2, 2, 1, 1. Why did that end up over there? I'm wondering if we did this first. Still 2, 2, 3, 3, 2, 1, 1. How does that happen? We don't need that here. The question is, so this is wrong. Something here is incorrect. I want to say it's less than k. It's got to be. So before we even begin partitioning, 2, 1, 1, 2, 3, 3. Okay. So greater than mid. So you swap the 1 with 3, swap the 1 with the next 3. This 2 we don't touch. And these 1s we keep going. I want to say that this is not right. Something wrong here. Because this 2 is supposed to end up over here. Now, am I crazy? So that's not right. Or at least doesn't do what I think it does. I missed something. I missed something important. Oh. That's what it is. Okay, got it. Yeah, duh. You don't go to the next element yet. Okay, that's why. Alright, of course. feel like a dummy. I feel like a dummy. Couldn't figure out what was wrong. Okay, these made sense to me, but this, yeah, okay, that makes sense now. So this was incorrect, or somewhat makes sense. I kind of should have been able to figure that out though, but the reason is if you're less than the mid, you want to swap that element. However, you don't want to go necessarily to the next element because the element you just swapped don't necessarily know where that goes. And that maybe should go here, right? Where I is, yeah, okay. That's something, you kind of memorize this a little bit, but yeah, the smaller elements you swap them over to the right side, but then you may want to swap that larger element to the left side, and you'll miss it if you increment j, which is what happened. Okay. So we can partition right on nums. It doesn't need to be array. I just thought maybe it was wrong, but it's not wrong. It can just be right into nums. So we don't need to copy this. It's going to be nums of. You could also, alternatively, you could say something like this, and then you can do excuse me. This is a little bit easier in terms of like how much code you gotta write, I guess. Fewer characters. Does that work? Yeah, that's better. I like that. Alright, let's see if that's correct. Okay, there you go. So this probably isn't much faster than just simply sorting it. But that's what I was saying before, is that this basically works the same way as sorting it. And then you can run this routine to map everything into the right place. And then so what you would do is now you can take this define. It's not really a way to. You really don't need a preprocessor directive. I don't know if you should have a function call though. Maybe it should be a preprocessor directive. You know, I'm not really sure. Maybe it is better to do a preprocessor directive. turning these back to integers. They're just easier to understand as integers. Although you could use them as pointers, I think, but yeah, it's a little harder to understand it as pointers. Okay. That's pretty amazing, though. Okay, something like this. And then we don't really need this anymore, do we? Wrong answer. Nice. Very good. I think you need to do this. No? Okay, there we go. What? Right. One. These aren't right. These are not right. What's going on here? What's going on here? That's not what I'm expecting. What's happening here? 111465. Oh, okay. So this should be, no, this should be here, not. Oh, wait. No. What? What is going on here? Oh, it's probably because I needed to do this. This shouldn't be an issue. Let me also raise the volume here while I'm whispering. Yeah, now that my voice is very low, let me raise the volume. Okay, I see the problem. to Preprocessor Directive. That's what it's called. There we go. That's what we want. Built in. Okay, how do we do? Yeah, now I don't need this anymore, I think. There you go. And this is extremely fast now. This is probably the fastest that you're gonna get. I want to get 100%. I didn't get 100%. 6 milliseconds. Gotta get 6 milliseconds. Come on. Come on. I think the fellow that got 6 milliseconds was, he did, so okay, so this is ultimately, this is the solution, right? Using three-way partition with a mapping built in. If we do, to get the fastest, the absolute fastest, we would do sort nums.begin, nums.end, using right, and do that, and then you just say when I say something like this, so we're going to start off at these odd values, nums of I, and then you do and then you do the same thing here. Does this work? I don't know. This might not even be correct. Oh, seems right. Okay, let's see if we can get the optimal runtime. One, two, three, four. 1, 2, 3. No, not quite. No. Alright, what if we remove this? Does it go faster? Is it still correct? Looks Looks like it might still be correct. Does it go faster? I don't think so. No? What if we do this? We optimize our loops a little bit. No? Okay. Really? How about this? Is that still correct? Optimize our loops a little bit. Oh, 12 milliseconds. It's close. No, 52 milliseconds. 12 milliseconds. We're getting closer. We're so close. Oh, man. No, doesn't do it, huh? Doesn't quite get there. We're so close, man. So 6 milliseconds is the fastest. Oh, we're so close. We're so close. What if we just go all the way back to this guy? What if we go all the way back? No, I don't think we're gonna get it. I don't think I can get 6 milliseconds, man. This is such a good question. 16 milliseconds, we're so close. We're so close. I wish I could like this again. Alright. Well, we did alright. We did okay. The solution I ultimately came up with was not so great. However, these other solutions are very interesting, very clever. I wish I had come up with something like that. There's no real reason to write quick select again, right? We have STL algorithm for it. Excuse me. What do I say here? What do we do? Yeah, we're doing all right, man. We're doing good. I mean, amazing. And I got a review of the three-way partition. I've seen it a few times now, but I forget it each time. That's a good one. It's one to remember. All right, when you see something larger, you have it, put in the right spot and move everything. So move the next element and move your larger pointer. See something smaller, move it to the smaller values and swap it with something over there, but that could also be a larger value. So you want to loop again and not necessarily go to the next spot yet. And then if you see something that's in the midpoint, you just skip it. And those are the three different operations. And that'll give you could prove that'll give you the right answer. Yeah, because what will happen is that I value that you're pointing to, if you're pointing to, you'll eventually bump into the, you'll eventually bump into the mid values, if the mid values need to be moved over, and they will be, right? You'll just end up swapping a mid value with a larger value as needed. Amazing. And then you can modify your three-way partition in order to get different sequences. That's really unbelievable. I mean, that's like, talk about human intuition. Pretty astounding. Didn't hit 100% though. We got so close. We got so close. All right, let me get going here. Yeah, so I was gonna do some other stuff too. I guess I forgot what I was gonna do, like quick select implementation and like a rewrite of whatever it was I ended up writing. But I'm just glad that I did actually get the solution, the one that's linear time complexity and expected linear time complexity on average linear time complexity, almost certain linear time complexity, and constant space. I'm just glad I got that. The way to do that though efficiently, obviously it was beyond me. However, I mean, it's not beyond my understanding, but definitely beyond my, I guess, creativity to come up with that kind of on the spot, or even a few days of thinking about it. That's amazing. I mean, there's nothing else to. I gotta hand it to Stefan, man. That's wild. And also, I'm noticing how high my volume was set. My volume is set so high. Let me go. Thank you all for watching. Talk to you all soon. Have a good. Let me just adjust the volume while I'm still here. Let me just adjust the volume while I'm still here, so that way this isn't like crazy high when I come back later. All right. Thank you all for watching, hanging out, saying hello. I do appreciate it. I'll talk to you all soon. Have a good rest of your night.